Now, a quick announcement for homework 2. I made the due date January, yeah.
January's good.
Yeah, January.
September 30th rather than 28th, because 28th is the very first class after I'm back from Europe. And if I want to give a little more time, like there are questions and stuff.
Get rid of the hangover.
What?
Get rid of the hangover.
Yeah, I also am useless the first day after a trip, so that'll be an interesting class. Yes, because I'll be flying all the way back from Greece. And then I pushed our due dates back a couple days too. So, okay, are we recording? Yes. All right. So today is all about, and hopefully I can do it all today, because Dr. Tiana said to cover different stuff next week. The existence uniqueness theorem. To prove that a general first order system has a unique solution under the right assumptions. And those of you in 560 will recognize some fixed point iteration items that were covered there. So this is section 3.1 and 3.2 in the text. So first, so we're considering a general first order time dependent, so in other words, non-autonomous system, and with an initial condition. Okay, and alpha is a vector. Okay. Now, what we can do is we can take both sides of this. We can integrate both sides. With respect to t, and we get this ODE expressed in a new form. That's the integral form of the system. So that would be just alpha, alpha of t is equal to the initial value, c, plus the integral from t naught to t, and then we fill in the vector field here, x of s, alpha of s, ds. So we can't do dt because t is a limit of the integral, so we just have to pick a different letter. So this, for proving existence and uniqueness, the integral form is much more convenient because instead of having two equations specified, ODE and initial condition, everything's wrapped up into one. The initial condition is automatically accounted for because if you plug in t equal t naught, the integral is gone, and you're just left with c like you're supposed to be. So we're going to just work with this. Now, in order to prove existence and uniqueness, we're going to do use an iterative process. So we're going to take an initial guess for our solution alpha, and then perform an iteration that keeps improving alpha until it converges, hopefully, to a solution of this integral form, which means it's also a solution of our original system. Okay. Actually, let me make sure that video people can get everything on the board. Okay. Okay. Now, those of you who are Star Trek fans, you can get your wisecracks ready.
Hey! I love him. He's my favorite.
Okay, I kind of expected someone to say that. For card iterus, the idea is, so we have some curve we'll call beta, and we define a transformation that takes a curve beta and gives you a new curve. So t of beta, so this is itself a new curve. And for any curve, you can evaluate that at t. So that's what's really going on. And what is t of beta? It's actually the right side of the integral form. C plus integral t naught to t of x of s beta of s. So the idea is, whatever curve you're plugging into a transformation, you plug in here, inside the integral. And then you carry out computing this, you plug it into a vector field, you integrate the vector field. And when you're integrating a vector, all that means is you're just integrating each component separately. So integral of a vector is defined in the most straightforward way you can imagine. And computing all this, you get a new vector function of t, and that's your new curve. So the Picard iterates are just a set of curves defined by t of beta, t of beta, which is the same as t squared beta. So I'll use that notation to indicate applying the transformation multiple times. T cubed beta, and so on, all the way to infinity. So you're applying the transformation t repeatedly. And this is actually what we'll do. This is how we'll solve this system of ODEs. We'll come up with an initial guess for beta, our solution, and then we just keep applying t to it and hoping that it converges. Because, so a curve alpha is a solution of our original initial value problem if and only if t of alpha is equal to alpha. Okay. So now we're characterizing the solution of our initial value problem as a fixed point. So we're saying alpha is a fixed point of this transformation t.
So like we did g of x star equals x star.
Yes, exactly. So t is playing the role of your g of x from that. Our goal, what we're going to tackle today is prove that t has a unique fixed point. So that is literally what we're going to prove. However, by doing that, this is equivalent to saying the initial value problem has a unique solution. Okay. So that's why we did all this. Like we go to integral form and then define this transformation t in order to have an alternative way of characterizing a solution. Because it's a lot easier to prove this than to try to prove this in any other way. And it's a lot of things from six-point theory, some things that those of you who are in 560 happened to see yesterday, and well, actually anyone who didn't take 560 isn't taking 560 now, they took 460 before. Yes, I'm sure it would have been forgotten. Like you took it 4 years ago, so. And you guys 2 years ago, so I can't blame you if it's forgotten. Okay. Now, before I erase the other board, okay, because we want t of alpha equal alpha to be a solution. So this right here is t of alpha of t. And alpha is described as being a solution to this, so you can see from this why they're equivalent, why alpha being a fixed point of t is the same as alpha being a solution of this integral form, and therefore is a solution of this system of ODEs, or this initial value problem. Okay. Now, okay, so now what I'm going to do is state the existence uniqueness theorem, and then hopefully during the rest of the time I can prove it. The only homework problem I gave in section 3.2 is actually proving something similar to the existence uniqueness theorem, but in a somewhat different context. So a lot of the same ideas apply, and that's why it's important to have some understanding of the proof. Okay. That I'm about to do. Okay, so first, what is the existence uniqueness theorem? Because the IVP doesn't always have a unique solution, not just any old IVP. We do need some assumptions. Okay. Oh, already spotted a typo in the notes, dang it. Okay. Now, it's still nice and rigorously, except for this one typo in the notes, but I'll just give you the main idea here. All right. So we're going to assume that all of the first partials of your vector field big X they need to be continuous on whatever domain you're considering. So that's the main assumption that we need to prove existence and uniqueness. For each initial point, so here's your initial time, here's your initial data, in your domain of your time-dependent vector field. So we're assuming that the first partial derivatives are continuous on that same domain B. Okay. So for each initial point, the IVP x prime is equal to big X of t little x. And in the notes, I forgot the dang prime. So, but something you guys are used to seeing by now. With this initial condition, x of t naught equals c, has a unique solution, at least near this point in your domain. Okay. So there actually is a global uniqueness result that's actually proved in a section. I'm not going to get into that today. We're just going to show that at least in a neighborhood of this point, if it's close enough to it, the solution really is unique. Okay. Now, in order to get into a proof, here's a definition I need. So I'm going to define the norm of any given vector x. And I'm going to define this as a magnitude, but I'm going to define the magnitude a little bit differently than you're accustomed to. Because normally you think of a magnitude of a vector is you sum up the squares and take the square root, so it's like Euclidean length. We could do that here, but it's easier for us to use this definition, where we just take the sum of the absolute values of the components. Now, those of you with enough numerical analysis background might recognize this, and anyone who took 610 recently, hint, hint. This is the vector 1 norm, as opposed to the vector 2 norm where we use Euclidean length. Okay, so that's one definition we need. Another definition we need is, I'm going to define a closed ball that has a center at this vector C and has a radius r. So this is a ball in n-dimensional space. And it's just a set of all points in Rn such that the distance between a point and our center C is less than or equal to r. Okay, now you could think of this like an n-dimensional circle or sphere, except distance is not measured in the usual way. Distance is measured in this sense. So in 2 dimensions, you would not actually have a circle. In 3 dimensions, you would not actually have a sphere. It'd be a different shape, but it's a similar idea. It all depends on what metric you're using to define distance.
Why would it not be this?
Because we're using the 1 norm instead of the 2 norm. Yeah, if this were a 2 norm, we'd have circles, spheres, etc. Okay. Now the thing is, our domain B, we're going to assume, for convenience, it is an open set. And what that gives me is that for any C in the domain, the ball centered at C and a radius r is actually contained in B if r is sufficiently small, because I need to stay within this domain, B, because that's where the vector field big X is defined. So I don't have to worry about that. So as long as I choose r small enough, I know my domain is going to be included in B. Okay. Now, this closed ball, because the key thing is, in my definition of a ball, I use less than or equal to, as opposed to strictly less than. It is a set that is closed, and it has a finite radius, so it is bounded. What do we call that from yesterday? Compact. The term that you will see in real analysis, I'm sure, at some point. Dr. Ding will bring it up. So what that means is the components of the vector field X themselves and the first partial derivatives, all of these have a maximum and a minimum on this closed ball. Okay. So this is a very important, and the reason why I can say that is they're continuous. Any continuous function on a compact set has a maximum and a minimum. In Cal 1, you had to find a maximum of a function on a closed interval. It's like that. But that applies in any number of dimensions. Okay. So what I can do is there exists some constant, I'll call it big K, such that the components of big X are bounded by K, and these first partial derivatives are also bounded by K. Because they all have their independent maxes and mins, but I can just choose big K to be the largest of all of those values, just for convenience, so I don't have to work with a whole bunch of different constants.
The chain could be like big X to the I and the small x to the chain. Is that
The reason for these are components of a vector field,
right?
so that's why I use a superscript. but these are independent variables. Okay, so this is, yeah, I should distinguish more. This is big X, and this is,
Is that the same over here too then?
yes.
That's
Big,
the
big X up top, little x down below.
Like the vector field X?
Vector field X. Sorry about that. Okay, I'll use this notation for vector field, even for the component functions. Yeah.
Small x and the
Yeah, the ones in the denominator are independent variables. Yeah, that's because Dank book uses x and x all over the place.
So the big X is a dependent vector.
Yes, the dependent vector. Okay. All right. So now, as a result of this assumption, that so now these are bounded by some constant k. That means that the vector field as a whole is bounded by n times k, because the vector field x has n components. Each component is bounded by k, but what do we do in the norm? We add up the n components. So we get n times k.
Is this a capital K, little k, doesn't matter?
When I put the things up top and below, that's the capital K.
Alright.
Yeah.
Alright. And the K though, that's what I said.
Oh, K is capital.
Oh,
I'll make that exaggerated. Oh, that's gonna get uglier. What?
I just said, oh no, sorry, I didn't
Oh,
say that out loud.
Okay, all right. So that's one thing we have. We have a bound in the norm of big X, and we can also have a bound on the norm of big X of t little x minus big X of same t little y. So I need to come up with a bound for this, and I'm going to run out of room. I'm not going to change this. I'm going to condense it. So you don't have to erase anything in your notes. Okay. So this is, by the definition of my one norm, I'm taking the same difference component by component. So this is still big X I of tx minus big X I again of ty. Right. But now what I can do with this is I can use the mean value theorem for each variable. So now I'm going to have a sum of partial of x, big Xi, with respect to little xj, evaluated at some unknown point, which I'll call zi, times the difference in these arguments, at least each component, xj minus yj. So these come to be little x and little y. So all I've done is, this is the mean value theorem applied with respect to each independent variable. This is an unknown point. So actually, I can say a little more about that. Z is on the line segments from little x to little y. So that's what I can say about this unknown point. All right. Now, each of these partial derivatives of big X are bounded by k. So, and also I have n of them. So this is less than or equal to n times k times the sum of these expressions here for each component. Now this condenses to n big K norm of x minus y. Okay. So that's the final result that I'm looking for there. So actually I'm going to summarize that over here because that's kind of cluttered. So big X of t little x minus big X of t little y norm is less than or equal to nk norm of x minus y. So ignore t right here because the t values are the same anyway. We're plugging in x and y, little x, little y, into the vector field, and with the difference is bounded by this constant times the difference between the arguments, x and y. This is saying big X of t little x is Lipschitz continuous. We've seen Lipschitz conditions in 560. It's the same concept, Lipschitz continuous. In the variable little x. I'm not saying anything about t. And the Lipschitz constant is this nk. All right. Now, as was seen yesterday in 560, Lipschitz continuity is helpful for proving the existence and uniqueness of fixed points. So that's why we're going to need that. Okay. I might actually be able to finish all this. Yes, I can. Well, as I'm going through the notes, a few more typos, so that's something to deal with after class. Okay. All right. Now, we're going to choose a constant, positive constant A. So that okay, I missed the definition earlier, but I can fill it in now. Okay, no biggie. So before I choose A, I'm going to choose first a positive constant B so that the interval of radius B surrounding T naught, my initial time, when taking the Cartesian product with my ball of center C and radius R, is contained with B. I goofed earlier that I wanted this ball to be contained in B. That doesn't really make sense because big B is a domain in Rn plus 1. It has your spatial variables and your time variables. So this would be defined on a slice of B. But if I take it in combination of a time interval, then it makes sense to talk about that whole thing, this whole Cartesian product being contained within B. Okay, so actually, I want to take a look at someone's notes. Okay. All right. Okay. Okay. So where I said that the ball B bar is in B if R is sufficiently small. You need to take the Cartesian product of the ball with this. So this needs to be included. So
So
this,
write it like that.
yeah. And you need B also to be sufficiently small. So there's, in other words, there's two radii in play. B is a radius in time, R is a radius in space. So you can choose both radii, and as long as you choose both radii sufficiently small, then this whole monstrosity is contained in B, because B is an open set. So I'm sorry about it. I left out the time part before, and because I didn't really need it here, but now I do. Okay. And the fact remains that this whole thing, this is a closed interval, so this is the compact set on which big X and the partial derivatives have a max min. Yes, when I was reading stuff in my notes, I just totally glossed over the time interval, and I can't do that. But everything else in the previous board, okay. All right, I'm going to temporarily go back over here. See, once I saw that I'm going to finish in time, I had to mess it up. Okay. So I just want to edit this. This Cartesian product with the ball is a closed bound set. This is compact too, but this is a compact set I actually need. And this has a max min on this the ball in space Cartesian product with this interval in time. Because, and I'll fix these two. All right. Okay, so let me just clean up a mess. All right, big B, so I'm repeating myself, but I want to really drive a point home, if you don't mind. Big B is a domain in n+1 variables, time and space. So it's an open set. We need basically a ball in all n+1 dimensions. So we set up this ball in space and this one-dimensional ball or interval in time. As long as we choose the two radii, B and R, to be small enough, because big B is an open set, it will be contained in B. Also, because I used square brackets and less than or equal to defining these, we're close to bounded, so we're compact. So these x and partial derivatives are defined on big B, space and time. They have a max min on this compact subset. Okay.
Can we think of B and R as like epsilon delta sort of? Open ball, open neighborhood.
You could, yeah. Well, except delta's for independent variable and epsilon's for dependent. These are all independent. Yeah, so it's
Right,
risky to do that.
Yeah.
okay. All of this still applies. It's just that it applied on space plus time, not just space. So everything here is okay. Okay, I apologize for mess. It's correct in the notes, I swear to God. Sorry, it has been a terrible week.
I like how you're just like frazzled about it, and we're just all like, that's okay, whatever.
I'm aware of that, and I really don't care.
I was just making a comment.
I know. Yeah, because I mean, that's nice and forgiving of you, but it really pisses me off when I screw up like that because I don't like to be that sloppy. But I am rushing because I want to get all this done in time and not leave Dr. Tian having to clean up a mess because. So I rushed and I got sloppy. Okay. So we've chosen B so that this works. Now we'll choose positive constant A, so that A has to be less than B. Also, A is less than our spatial radius R divided by NK. And also, A is less than 1 over NK. Because R could be less than or greater than 1. We don't know, so that's why we put in both these conditions. So R and NK and B are all fixed constants, so we can always choose an A that's smaller than all three of these. Okay. Now, this is going to be interesting notational quagmire. I'm going to call this set C tilde, because otherwise writing on the board I'm going to have a conflict of symbols. It is a set of curves. So beta is still a curve, and it maps this time interval t0 minus a to t0 plus a. So I'm working within a subset of my previous time interval. And these are curves in Rn. And actually, not just Rn. They're mapping into the ball, my spatial ball. And they had to be continuous curves. Okay. So I have this whole family of continuous curves that maps my smaller time interval into my spatial ball. Okay. Then I'm going to let beta be some curve in this set. And I'm going to let t belong to my smaller time interval. Okay. And what that's going to give me is the following. If I look at taking my Picard iterate of beta, plugging in t, I want to see how far away this is from my center, my spatial center C. Okay. So what I can do is, using the formula for the Picard iterate, well, C is in that formula, so that's going to cancel out. The only thing that's left, because recall, T beta is C plus the integral of x of s beta of s ds. So I'm just using this. So I move the C to the other side, and what I get is a sum of integrals of each component, because this is a vector. And I have each component of my vector field. Okay. Now, what I can do is, I can move the absolute value inside the integral. As long as I change this to a less than or equal to. Okay. Now, all of these components of big X that's less than or equal to big K. So this is less than or equal to n, because I have n components, capital K, because that bounds the integrand, and times the difference of the limits, the width of this interval, t minus t naught. Okay. Now, t minus t naught is less than or equal to a, because t is in this interval. So this is less than or equal to n big K little a. But n times k times a is less than or equal to r. Actually, strictly less than r. Because of that. So based on my assumption about a. Okay.
So numbers,
Yeah.
how did we get, I'm sorry, I know the reverse, but how did we get that nk times t minus, I understand the t minus t naught part, but the nk,
Well, each of these is bounded by k.
right, and n times.
Yeah, n components.
Right.
Yeah.
Okay.
Okay, now, this actually tell us? Well, it means that this point, t of beta of t, is a point inside our spatial ball. So, therefore, t of beta belongs to c tilde. Okay, because any curve that maps this time interval into the spatial ball is in c tilde. Beta, we're already assuming it is. T of beta also is, because any point on the curve is a distance less than r from the center. So it's contained within that ball. So another way of stating this is that t maps c tilde into itself.
So beta is also in C tilde, right?
Beta is assumed to be. We started with that. And now t of beta is 2. So anything in c tilde gets mapped by t into c tilde. Now, that actually proves that t has a fixed point. Any continuous mapping, which this is, that maps a certain domain into itself has a fixed point. From 560, it's the same as Brouwer's fixed point theorem. It's the same kind of result. So that's progress, but we need to show not only is there a fixed point, is that it's unique and that we can actually converge to it. Oops, got it. All right. Now, for convenience, I'm going to choose a constant, define a constant q to be m times k times a. Now, based on the assumptions I made about a, I can say that q is less than 1 because I assume that a is less than 1 over nk. Okay, so that's one definition I need. And I also need this definition. I'm going to let C, as opposed to C tilde, very closely related, this is a set of all curves that map the same spatial interval, but just map into Rn. And they have to be continuous curves. Okay, so C tilde has curves that are only they only occupy the, when you traverse a curve, you stay within the spatial ball centered at C. Here you can go anywhere. All right. And I'm going to, if I take any curve in C, I'm going to define the norm of a curve to be equal to the supremum of the norm of alpha of t for all t in my over all t in my interval. Okay, so the idea is if I plug in a specific t, this is the sum of the absolute values of my components, because this is a vector. But that's for a specific t. So this is my usual 1 norm that I've been using. But now if I take the largest of these over all t in my domain, so supremum is not exactly the same as the maximum. You guys have been seeing this in real analysis, right? The supremum?
Yeah, upper bound.
Yeah.
Okay. Yeah. So it's close to being a maximum. It just doesn't have to be in a set. And that's how I define the magnitude of a curve over its entire domain. Okay. So now I'm going to look at this. T of some curve beta of t minus t of some other curve alpha of t. Okay, so using the definition of a Picard iterate, this is a sum of the integrals over all the components of these curves. So that's going to be xi of s beta of s minus big Xi, oh, and I already have the absolute value, so s alpha of s ds. Okay. Now, as before, I'm allowed to move the absolute value inside the integral as long as I make it less than or equal. So that's all I've done here, is move that absolute value inside. Okay. Now, so now what I can do is I can actually move the summation inside also. And in fact what I have is it's still the same integral of the one norm of x of s beta of s minus big X of s alpha of s. And that's just using the definition of norm, because here I have all the components, here I just put them together and sum them up. Okay. Now, using a result that I had before, I had something like this, a big X with one curve plugged in minus big X with a different curve plugged in. Yeah, that was done earlier. So using that, I can say this is less than or equal to n k, because okay, I did this actually, yeah. Nk beta minus alpha times the width of the interval t minus t naught. So this comes from what I did earlier.
The x's were less than x.
Yes. Oops, this is big X.
Big X.
Less than or equal to nk, the Lipschitz condition. That's what I referred to it back then. So all I did was I applied this over here. That's where the nk comes from. And then the difference of these arguments times t minus t naught. But t minus t naught is less than or equal to a, because I'm still working within that interval. So this is less than or equal to nka times beta minus alpha. Okay. Now I've defined nka to be q. So now what I can say is, I'll just write it in here. The norm of t of beta minus the norm of t of alpha is less than or equal to q times the norm of beta minus alpha. And q is strictly less than 1. So what we say is t is a contraction on VSET, okay. All right, and beta and alpha are, okay, it's actually, as far as the results that I used earlier, I have, yeah. Actually, I really only needed to be a contraction on C tilde, because T maps C tilde into itself. But now we know that it's also a contraction. So it, this is the same notion of contraction that we had, it comes up also in 560. That's useful for proving uniqueness of a fixed point. Okay, so now we can finally start reaching the end game here. Okay, so now I'm going to let beta be any curve in C tilde. So it maps our time interval into our spatial ball. So if I apply my Picard iterative transformation, k plus p times the beta, and look at the difference between that and tk of beta. Okay. Now what I can do is, in each case, I can factor out one of the t's. So that's t of k plus p minus 1 of beta minus t applied to t k minus 1 of beta. All right. And because of the result that I had just a second ago about t being a contraction, that is less than or equal to q times the difference of these arguments to t. Tk plus p minus 1 minus tk minus 1 of beta. Okay. So now what I can do is I can continue factoring out powers of t. And every time I factor that out, I get another factor of q. So if I carry out what I just did, k times, I end up with q to the k over here, and I get t to the p of beta minus just plain old beta. So I factored t out k times and gotten k factors of q because I have a less than or equal to now. Okay. Now I'm going to I'm going to specialize to the case where p is equal to 1. So I have t to the k plus 1 of beta minus t to the k of beta is less than or equal to q to the k t of b minus t of beta minus beta. So this is just the previous result reduced to for a case where p is equal to 1. So I actually need both of these for what I'm going to do next. All right. So now that I've come up with this expression, I'd like to have an upper bound for that. So t to the p of beta minus beta norm. So what I can do is I'm going to pull a major add subtract trick. So t to the p minus t to the p minus 1 plus t to the p minus 1 and so on. So I just keep adding, subtracting lower powers of t all the way down to so minus t of beta plus t of beta minus beta. So I just add subtracted all these times, so nothing has really changed. Now I use triangle equality like a zillion times, well, p times, and pull these apart, and I have a less than or equal to. So t of p minus t of p minus 1, close the norm, plus norm of t p minus 1, minus t p minus 2, and so on, all the way down to t of b, I say b, I'm really in beta, t of beta minus beta. Okay. Now, I can use this result in each one of these terms. So for instance, this first one is less than or equal to q to the p minus 1 times t of beta minus beta. The next one is less than or equal to q to the p minus 2 t of beta minus beta. And so on, all the way down to t of beta minus beta. So now I have t beta minus beta in every term. And I can factor out the q's, or powers of q. So I have q to p minus 1 plus q to p minus 2, and so on, all the way down to q plus 1 times t of beta minus beta. All right. Now, this sum of powers of q, what do we call that?
It's a series.
What kind of series?
Some of the, it's a geometric.
Geometric series. And this is a finite one, so we use a formula for a partial sum. So this is less than or equal to 1 minus q to the p minus 1 over 1 minus q t beta minus beta. Now we can upper bound this. This term we can ignore because we just want an upper bound. So this is less than or equal to, because q is positive. So it's 1 over 1 minus q, and q is less than 1, times t of beta minus beta. Okay. Now, I'm going to take, so actually I have 3 results on this board. So now I can combine this result up top with this result down below and get something more useful. And I'll repeat what I'm combining just so you can more easily see.
Why did the q go away in the numerator? Because it's less.
Oh, just because 1 minus q to the p minus 1 is less than 1.
Right.
And all I care about is an upper bound. Because I can replace that by any expression that makes it bigger. So in fact, I could have said strictly less than, but there's really no need to. Okay. Now, from the results I have, t to the k plus p of beta minus p to the k of beta less than or equal to q to the k t to the p beta minus beta, and t to the p of beta minus beta less than or equal to 1 over 1 minus q t of beta minus beta. Just putting the two together, I have t to the k plus p of beta minus t to the k beta is less than or equal to q to the k over 1 minus q t beta minus beta. Okay. Do you have any better chalk? Not really. Okay. Now, what follows from this is this sequence, t to the k applied to beta, for all k from 1 to infinity, is called a Cauchy sequence. And a Cauchy sequence, what I mean by that is, for any epsilon greater than 0, there exists a k naught such that for all m and n greater than or equal to k naught, so above a certain index threshold, the difference between t to the m and t to the n can be made arbitrarily small. So that's the definition of a Cauchy sequence. And because what's happening is, because as k increases, q is less than 1. This is going to 0 as k goes to infinity. So I can take, so this right here is a fixed constant. And here we have something that's going to 0. So for any epsilon I choose, I can find a k large enough so that q to the k is small as I want it to be. And p can be anything. So you can think of k as being my n down here, and this is my m. Because the key part is p can be anything I want. It doesn't matter what p is. Okay. The importance of it being a Cauchy sequence is that this sequence, yes, it has a limit. So the limit as k goes to infinity of t to the k of beta is some curve alpha. Okay. All right. I'm down to the last page, and it's only half a page. So I think I can do this in the time that I have left.
I don't think I've ever seen you write so much in class.
And I hope never to again.
Cool. I'm impressed.
I was,
I looked up, I was finishing writing one line, and I looked up and you already had half that board written, and I'm like, I didn't know you could complete that fast.
under enough to rest, yes, I can.
Just saying.
Now, is this limit alpha in our set C tilde, which is a set of all curves that map our time interval into our spatial ball? Alpha is in our set C without the tilde because it's a continuous curve defined on our time interval. So we just need to know it's not only in C, it's also in C tilde. So let's find out what happens. Alpha minus C. So the distance between our curve alpha of t and our center C is less than or equal to, and I'm really doing the add and subtract trick and our time inequality, triangle inequality. So I'm adding and subtracting tk of beta. Okay, and then I pull them apart and use a less than or equal to. Now, this part here goes to 0 as k goes to infinity because alpha is the limit. So what that means is, and this part right here is less than or equal to r. And the reason for that is, okay.
So alpha is in C,
Um,
so it has to be in the ball.
well, also now beta is in C tilde. We're assuming that. So what's happening here is Now, the reason why this is true is because T maps C tilde into itself. So beta is already in C tilde. So if we apply T to it, we get another curve in C tilde, and we keep applying it. We stay in C tilde, so it has to be within R of the center. Okay, so this whole thing, so what that means is, alpha minus C is less than or equal to R because the rest of it's going to 0. What?
I can't tell if that's an epsilon. For a
Yeah.
second I thought it was just be T. But it's
This is an epsilon.
Oh,
I thought you were talking about those.
because
Oh, yeah, that's what I thought you were. I was like, wait, what are you, okay.
Yeah, I thought that
Okay.
was like.
Sorry about that.
no, it's okay. I'm just trying not to stop you.
Okay.
So next time, just keep going.
Okay. No, I hear a chatter. It's like what? Yeah. So, okay. So alpha is within distance R of C. So that means that alpha is also in C tilde. So, so since all the Picard iterates are in the ball, are mapped to the ball, the limit is also mapped to the ball. Okay. Next, T is a continuous mapping. So if I look at T of alpha, well, that's the same as T of the limit as k goes to infinity of T to the k beta. But I can move the T inside because T is continuous. So now I get T to the k plus 1 of beta. But the limit of T to the k is the same as the limit of T to the k plus 1. So that's still going to be alpha. So what that means is T of alpha equals alpha. Alpha is a fixed point. And that's what we want. It means it solves the initial value problem. Okay. Now, there's only one thing left to do, and then I can bring this infernal lecture to an end. And I have 4 minutes to do that. Okay. I've shown a solution exists. The only thing that's left is to show uniqueness. So if gamma is also a solution, so T of gamma is equal to gamma because it's also a fixed point because the two statements are equivalent. So here's what we look at. Let's look at the norm of alpha minus gamma. Well, alpha and gamma are both fixed points. So that's the same as T of alpha minus T of gamma. But T is a contraction. This is less than or equal to Q times the norm of alpha minus gamma. However, Q is less than 1. So basically I'm saying that norm of alpha minus gamma is less than the norm of alpha minus gamma. The number cannot be less than itself. That would be weird. So that means the only way it can happen is that this has to be 0. So alpha has to equal gamma. So that is uniqueness. Okay. So to summarize all the crap that went on here, what we did was we re-described the initial value problem as an equation of a form solving T of alpha equals alpha. We showed that T maps a certain domain into itself, a certain set of curves into itself. We showed that T is a contraction. Those two together are enough to conclude that through some other manipulations, that t has a unique fixed point, alpha, and because it's a fixed point, it is a solution of the initial value problem, and because the fixed point is unique, existence is unique, the solution of the IVP exists and is unique. So this illustrates, actually I made this comment in 560 yesterday, how fixed point iteration is one of the most powerful devices in all of mathematics for proving the existence and uniqueness of solutions of whatever kind of equation you want to deal with, and also actually solving that equation. Because if you don't have any other way to solve it, you can try setting it up as a fixed point iteration. If you can find a contraction for your basically your function g, or your mapping t, that it's all the same thing, then you have everything you want. You have a solution, you can prove uniqueness, etc. So it's actually useful as a theoretical tool and as a practical tool. In fact, actually, I could easily spend a whole semester teaching a course on just fixed point theory. It's like a branch of functional analysis. So any of you PhD students, well, actually we don't have any PhD students in here, right? We don't. If any of you become PhD students, you can take 771, and it probably will come up there. We'll see how it goes with the one homework problem from 3.2, where you're taking certain items from this proof, and that this proof is in the book. It's all laid out there. To see if you can adapt those things. And you're using definition of limit and continuity, all those things that are probably being covered in real analysis. But this homework is chapter 3, so it's not due for a zillion years.
I don't know, I'm not even worried about it.
Sometime in October. So. Okay. Yes.
So there's a question sequence. Can we think of TFT and the subsequences of that?
Or still individual elements. Yeah.
But, we were something else, converted sequences and subsequent,
but like any balance sequence and conversion subsequence, that sort of thing. I think it'll cause more confusion than help.
okay.
Oh, I have to stop taping now.